I want you to graph two functions. F of x is simply x, right? And g of x is 1 over f of x, which is what?
It's the hyperbola, but
Yes, but I mean just what
just
is
1 over x.
just 1 over x, right? I'm not, like I said, I'm not being deliberately tricky with this. There's rhyme to my reason, because I want to see what happens if we have the graph of one function, which should look something like this. So I'm doing f of x in pink. And I'm going to go ahead and label it. Why not? There's f of x. And then you should have drawn something that looks like this, right? And also over here, right? That's what g of x looks like. And g of x is 1 over f of x. Everybody remember that? Did everybody get this? Right? There's nothing tricky going on here. But I want this up on the board because later on this is going to help us. Okay? So for right now, we're going to leave that right there. And we'll come back to it soon. Okay? All right. So before we really get into what we're doing today, I do want to go over a definition. I brought it up before, but here I want, it's useful to actually just kind of talk about it a little bit. Definition: a function is periodic. So that's the word we're defining. The function is periodic if there is a real number k, okay, so a real number k, and k is positive, such that the function t plus k equals f of t, and here we go, for all t in the domain of f. Okay? So you have some function. So like for instance, g, there's one number is not in the domain of g. What's that one number that you can never plug into g? Because remember, domain is the allowable inputs. Zero. So g is not in the domain, but all the others work, right? So that's all we mean by this. So we're only concerned about the domain of f here. And for every number that is in the domain, for everywhere where this guy is valid, then this is what it means. And so let's kind of pick this apart a little bit. Oh, and one more thing. The least such number, k, is called the period. Okay? So as we do in math, I give you some definition that's kind of like, what? And then we're going to talk about it a little bit. Okay? So, for instance, I said that sine was periodic. And basically what all this means, this is just a mathematical way right here of saying it repeats over and over again. Okay? So if I graph sine t, so that's what I'm going to do here. I'm going to graph the function sine of t. We know that it goes up and it comes back down, and it goes up and it comes back down, it goes up and it comes back down, and so on and so on. It also does it in the other direction. It goes up to 1, it goes down to -1. Okay, it also goes in this direction. It goes down, it goes up, it goes down, and so on and so forth. Now, watch what I'm about to do. This is the way that I do this. I'm only going to mark, like I could, if I wanted to, I could put pi over 6, pi over 4, pi over 2, and so on, all the way around. The only things I want to do are, I want to label these parts and these parts here. So, this one, what is the first one? Where does it reach its max? Its first max?
pi over 2.
Pi over 2. So what I'm going to do here, and so I know that that's the spacing for each one of these, I'm just going to count by pi over 2 as I do this. I'm going to go 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, which is 2 pi, then 5 pi over 2, 6 pi over 2, which is pi, 7 pi over 2, 8 pi over 2 is 4 pi, 8 pi, 9 pi over 2, finally 10 pi over 2, and so on and so forth. Going backwards, I'm going to do the same thing. Negative pi over 2, negative 2 pi over 2, negative 3 pi over 2, negative 4 pi over 2, which is just 2 pi. Okay, so what is this definition telling us? So, now, all this is saying is that does there exist a number so that no matter what value of t you're plugging in, basically this is just saying it's going to repeat after however big that is, right? So, for instance, if we take one of our t's in the domain, which happens to be 0, 0 is in the domain, what's the domain of sine? What are the allowable inputs for sine? Everything. All real numbers. Both sine and cosine. The way we defined it yesterday, I said for all real numbers, you do this thing with a circle, right? You just keep moving the circle around and blah, 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 blah. And so the way we've defined it, it works for all real numbers. Okay, so the domain is all real numbers. But here's the thing. Take one of those. Now, we're going to start going along and look until it repeats, until you get the same value. But be careful, because look, you get the same value here, but now as we move over, do we get the same thing? No, so that's not the least such number k that does that, right? We have to keep going until we get to here, and now we can see, if you take this and move this to any other t, right? So this is my k right now. We add k to it and we get this. We're back where we started. And now for any t, we slide along and oh, lo and behold, right, we end up with the same thing. If I move by this much, we have the same. If I move again by this much, we have the same thing, right? That's what this is saying. It's just a mathematical way of saying it. Now, while it's true that this does repeat after this far, the period is not 4 pi. Because it's not the least such number k. So it's true, what I'm saying here, is it's true that sine t plus 4 pi is indeed the same thing as whatever sine t was. You take 4 pi, and let's say we take our t to be this number right here. You'll get the same thing. You get the same output, yeah, but that's not the least such number. We could do that, we could do one better by shrinking it down to 2 pi. Okay? Does everybody get that? So this is just a definition. It's in your book. It's good to know. This is like the mathematical way of saying it repeats over and over again. like that's how you do it, right? And so we would say then the period of sine is 2 pi. I'll probably abbreviate it like this a lot. PD for period. The period of sine is going to be 2 pi. What's the period of cosine? It's also 2 pi, yes. Both sine and cosine have a period of 2 pi. Now check this out. Look, I already said it's true that you add 4 pi to it and you get back to where you started. 5 pi doesn't do it, but if you do it with 6 pi, it works. So in other words, what I'm saying, what I've just written here, and I'm trying to write here, is that sine t is the same thing as sine t plus 2 pi. It's the same thing as sine t plus 4 pi. It's the same thing as sine t plus 6 pi. And so on and so on and so on. And in general, it's the same as sine t plus 2 pi times n, where n is any integer. It's just a good fact to know here, where n is any integer. Can integers be negative?
Yeah.
Does it work if they're negative?
Yeah.
It does, right? Because check this out. Look, let's plug in a -1 for n. And lo and behold, you end up back here. And yep, is that the same thing as that? Yep, and if you slide back, I didn't draw it all out there, but if you were to slide back any distance or slide forward any distance, it works. Ditto, the same thing's going to come back at minus 4 pi, minus 8 pi, all even multiples of pi. And indeed, I'm sorry, all even, but yeah, I guess all even multiples of pi, but you know what I'm saying. Same thing's true for cosine. Cosine t is equal to cosine t plus 2 pi times n, where n is any integer. This is just a couple things I wanted to get out of the way. It's not a big deal, though you will certainly see this stuff again. But it's not what I'm concerned with today. So, what I want to do today is I want to graph the rest of the trig functions. We've already graphed sine and cosine. Now what I want to do is graph the others. And do I want to do that up here? That's a good question. Give me a second to see how I want to set this up. I just will do that because we're going to end up going into that. So okay, all right, I want to draw this again. I'm not going to do this whole thing, but let's just get sine going on here. And I want to take my time for this, because this will be, let me do this. So here's, so on. Okay, so let's get out of here. Okay, so I want to, first I'm going to draw the sine graph. So starts at 0, goes up to 1 at pi over 2, comes back down to 0 at pi, goes down to negative 1 here at 3 pi over 2, comes back up to where we started at 2 pi. Goes back up to 1 at 5 pi over 2, comes back down, and goes on like that forever and ever and ever. Okay, on the other hand, it goes down to negative 1 over here, comes back up to pi right there, comes back up to 1 right there, and so on forever. Okay, so that's sine. What I'm concerned about right now, since that's sine, I want to graph 1 over sine.
So cosecant.
Yes. So I'm going to graph here, and I'm going to do it in blue. I'm going to go cosecant. Now check this out. We had a name for what it's called when this happens right here, when something blows up and splits. There's a name for, what did we call that vertical line? It's also, we also have a horizontal line for where it happens.
Start with an E?
Starts with an A.
Asymptote.
And those things occur whenever you divide by 0, which we can't do. It's undefined there, right? Like in our class, we can't define division by 0. And so, and interesting things happen here, right? If you try, because look at what happens. Look at what happens with f of x. When f of x goes to 0, 1 over f of x does some funky stuff. And it's not that it just blows up, right? That both sides go up. It depends on what side of this you're on, right? So, but first thing I want to do, because I want to graph, my goal here is to graph cosecant x. And so it makes sense to me to figure out where these asymptotes are going to be. And I would suggest that with cosecant and secant, that actually with all of them, every one of these we do, let's find the asymptotes first. So You tell me, where are the if we're going to be dividing by sine x, and if this is sine x, where are my asymptotes going to be?
Oh, at pi.
There's going to be one at pi. So I'm going to go ahead and draw that. There's going to be an asymptote here. Because we see what happens when you try to divide by
all
0.
The multiples of pi.
All
the even.
And odd, right? Because that's an odd multiple.
Oh, yeah.
So basically, and I'm not trying to look. I'm not looking for a formula here, but it's just I'm just looking at the graph, and wherever that graph of sine touches the x-axis, we're going to have an asymptote. Okay. And
So there's infinite asymptotes.
Oh, there's infinitely many asymptotes. Okay. Okay. So that's one thing to notice. Now here's the thing. There's another interesting thing that happens. What happens to cosecant x where sine x is equal to 1? What is, in other words, I'm saying if sine is equal to 1, then cosecant is equal to what?
1
over 1, which is just 1. So in other words, it's not going to move.
So they intercept all the ones. Like the one over.
Kind of like this, where our input here was 1 and our output here was 1, like with f of x, well that hasn't changed here. That happens to be where those two functions intersect. Ditto at -1, right? Look at that. You plug in a -1 into f of x, you get out a -1. But then if you divide by that, 1 over -1 is still equal to -1, right? So I'm going to suggest that the way to deal with cosecant and secant is to get those points first. So wherever sine is equal to 1, cosecant is also equal to 1. So we're going to be right here. Cosecant will have a point right there. It'll have a point right here. It'll have a point right here. But also, like we just said, ditto with -1. You take 1, divide by -1, you're still at -1. Okay? So cosecant is here, and here, and so on and so on and so forth.
So it's just gonna go. Is that gonna be a parabola?
It's gonna look like it won't be, but it will look like it will kind of look like. So okay, now let's figure out what's gonna happen here, because it's gonna depend on a couple different things. So first, let's just look at this picture right here. As f of x comes down through positive numbers, right? So f of x is approaching 0, but it's doing so by going through positive numbers on the right-hand side here. So like for instance, when x is equal to 1/2, the output of this is equal to 1/2. But then if you take 1 and divide by 1/2, what do you have? 2. That's why this thing shoots up, right? That's why it looks like it does. If you get down here to 1 over 10, right? You plug that into f and you get 1/10. But then you go 1 over that, we get 10. And that's why this shoots up so high. And so you can see when you take positive numbers and they're going down towards, they're approaching 0. We're going to say this, I'm going to put this up on the board, we'll define this officially. They're approaching 0 from the right, then what happens is this graph blows up. It doesn't blow down, it blows up, right? Which we're going to say it increases without bound. There's no bound here. If you try to say, well, it's never going to get bigger than 1,000,000, well, yeah, eventually you're going to get down to here, to like 1 over a couple hundred trillion, and then when you divide by that, it's going to get even bigger. There's no number that ever bounds this. It goes up forever and ever and ever. Okay? And that's kind of, let's just look at what's happening here. That kind of looks like that, doesn't it? Qualitatively, it's about the same. As the values of sine come down this way, they're getting closer and closer to 0 from the positive direction. So then if we go 1 over that amount, it's going to go up like that. And so on this side, it's going to qualitatively look a lot like this. It's going to come up like that. It's going to curve up. Now, we don't have the chops to prove this in this class. You'll learn this in calculus. Oops. But you can show that this thing does flatten out like this and then goes up like that. It starts flat and moves its way up.
What do you mean starts?
So it doesn't, there at the point, it's flat. It's not a bend or anything like that.
Yeah.
It doesn't come down and then come back up. It's, the slope there is 0. If you wanted to draw a line and touch at one point, call that the slope, that it would be 0. Okay? So, what about going in the other direction? What do you think is going to happen?
The same thing.
The same thing, right? Because what's going to happen, you're getting, down here you're at like 1 over 10, right? Well, then you're going to be up here at 10. You get closer, you're at 1 over a million. Well, then you're going to be up at a million. This thing works its way back up like that. That's what cosecant looks like. Now, let's look at this.
Wait, it just repeats.
It's going to repeat over and over again. But let's look at what happens when we're doing negative numbers. So in other words, if we're approaching from the left, okay, as we approach from the left-hand side of 0, because here's 0 in x, right? Like the x-axis. 0's right there. If we're on the left-hand side of 0, and we're heading in this direction, and we're doing this type of thing, well, now we have negative values, don't we? So if we're at -1/2, the output here is -1/2. And if we go 1 over -1/2, what do we have? -2. And so it comes down here to -2. Again, and you can kind of see what's happening. I'll just do one more of these. If we're at -1 over a million, and we go -1 over a million, then we get to what? If when we divide by it, -1 million. And so you could say, and it will be said, it blows down. Like this one blew up, this one blows down. They actually do say that. But to be more precise, we'd say that as x approaches 0 from the left, g of x decreases without bound. And we can see that that's kind of what's happening here. In fact, it looks very much like this pink function right there. And as we go closer and closer that way, we're getting smaller and smaller negative numbers. If you divide by a smaller and smaller negative number, well, you end up getting this type of thing. Ditto as we go this way, right? As you get smaller and smaller negative numbers, I mean smaller in magnitude, they're like -1 over 10, -1 over 50, -1 over a million. They're getting smaller in magnitude. When you divide them, they get bigger and they're going to blow down. Like that. And now we just continue this picture. Okay, so that's going to do this right here. That's going to do this right here. And I'm telling you, if you ever have to graph cosecant or secant, the way of doing that is to draw sine or cosine and then just up on the top, like that. Any questions how I got that? This right here is cosecant x. That's what it, cosecant x.
They never touch each other, so it's just a bunch of different...
And there's a bunch, and so what's the domain of cosecant x? Or in other words, what are the allowable inputs? And rather, what are the unallowable inputs? What can we never plug in?
Any multiple of pi.
Any multiple of pi. 2 pi, 1 pi, 3 pi, all of them. So we could say then the domain of cosecant.
How would you say that?
Yeah, the domain of cosecant x. Well, there's a bunch of ways you could do it. You could just say, if somebody asked you what's the domain, you could just say x not equal to any multiple of pi. So pi times n, where n is any
You can't do
integer.
any interval.
You could do, yeah, no. Well, you could try. It would be, it's not that bad, but you could do it. But you could say, like formally here, you could say x, the real number is x, such that x is not equal to n pi, where n is any integer. That's how you do that formally. I'm not going to be too much of a stickler about that. If you just tell me that right there, I'll know what you mean. Like, well, in our class, we're going to take this as this part right here as shorthand for this whole thing. Okay, like we're not going to worry too much about this big formalism here. And n always going to be an integer in our class. I'll understand what you mean if you just write n. Okay, as long as you guys know what you mean by that both positive and negative ones work, right? Negative 1 pi, negative 2 pi, and so on and so on and so forth. Okay, now let's talk about this. So, I was talking about approaching stuff. So, these functions here, okay, this is what the ones we're going to talk about right now. F and g. F was just plain old x. G is plain old 1 over x. But that's what we're going to say. So, mathematically, we could say this. As x approaches 0, now watch what I do here, from the right. That little plus right there means that we're approaching it from the right, or from the positive values. So as x approaches 0, from the right, going down through positive values, then we're going to say, what does f approach? Look at f, see what happens. What value does it get closer and closer to?
0.
0, right? There's not much going on there, right? Ditto from the other side with this guy. As x approaches 0 from the left, f of x approaches what?
0.
Also 0. Doesn't matter with f, doesn't matter which way you're going, this guy's in both cases going there. Now, just as a side note, this won't be in your homework, but like, if it's the case that you get to the same place, whether you go from the left or you go from the right, then you're justified in saying, as x goes to 0, without specifying right or left, you could say f of x goes to 0. But that's not the case with g, is it? Right? It does matter which direction you approach 0. Because let's do this. So, as x approaches 0 from the right, g of x goes to what?
Infinity.
Positive or negative?
Positive.
Positive infinity. And that's what we're going to write there. Now, technically, the way of reading this would be to say, as x approaches 0 from the right, I think your book says something like, it might say, through positive values. I've never heard that anywhere else. Every math class I've ever taken approaches from the right. And certainly in calculus, that's how you're going to say it. As it approaches from the right. G of x, we don't say approaches infinity, although that is what it means. We say g of x increases without bound. Okay, so as we go to 0, from the right-hand side, we see g goes up to infinity, or we could say g increases without bound. Similarly, as x goes to 0 from the left, g of x goes to what?
A negative.
Negative infinity. But we would say, as x approaches 0 from the left, g of x decreases without bound. That is how you would say it officially. But like, if we're talking, I'm just like, hey, where does this go? You could say, it goes to infinity. I'll get you, right? Like, that makes sense. And you'll notice these are not reconcilable. These are two wildly different directions here. Unless you do a complex analysis, but that's different. We're not doing that. You could make them the same place, but we're not doing that in this class. They're wildly different. And so, we can't do the same kind of thing. We cannot leave this unspecified in this case. Now, you're going to see in your homework is they're going to give you stuff like this, although it's going to be one of the trig functions, but it'll essentially be like this, where either way you approach, like with f, either way you go, you're going to get to 0 with f. Doesn't matter. You could just say it this way. But your book is always going to give you a specification regardless. So, just so you know that. And I think I have an example I wanted to do. Yes, right here. Okay, so here's an example from the book. I want to get this out of the way, give myself a little bit more room here. And all your homework is just this. This is all your homework is, but you will graph each one of these. So help me, you will graph every one of these. So this is number 28. A says, as x goes to pi from the right, sine x goes to what? And that's the blank right there. You have to fill in the blank. Now, we've already drawn sine x, so I expect that for this problem, although that one's not a sine, it's the odd ones, but if you have this problem, I expect this to be drawn. Now, you don't really need, it's good to have at least one full period drawn, and in this case, since it's talking about pi, I would accept it if you just drew that much right there. But let's try to keep one full period, depending on where you are, okay? Any questions on that? One full period for each one of these things that you're going to draw, at least one full period, depending on wherever you are.
And label it, label all the...
It's good to label all that stuff. It's good to label your maxes and your mins. It's good to label where it goes through right there. Okay. Any other questions? Okay, good. So, what happens here? As x goes to that, what value does sine go to? What's the output?
Wait, no.
Sine's the black one.
Yeah. 0.
0, because right? This is how I imagine it. It says, this is what goes through my head when I see this, okay? I see, okay, x is going to this. So I just imagine, okay, x is going towards this direction right here, right? And then I imagine, well, what happens with sine? Well, he starts moving along like this. And so what value is he approaching as this guy gets there? Well, he's going to 0, right? And that's literally what goes through my head. As I see one of these types of problems, I just imagine I'm running along here, and then I ask myself, once I get to that goal, where am I going to be? I would be at 0. And remember, when you see this refers to the output value of the thing. So in other words, the height here, or the y value, if you like. If you like, you can think about this, sine x is your y value. So it's asking, as x does this, what does y do on the graph of sine? Okay. The next part, that's why I did this. The next part says, as x approaches pi over 6 from the right, sine x goes to what? Now you can't just look at this and see what it's going to do. That graph is not going to help you with this problem. Although it can help you in this sense. You could say, where is pi over 6? Well, it's between, yeah, it's somewhere in here, right? I'm not going to be exact here, but pi over 6 is somewhere over here. And so this output has to be somewhere between 0 and 1. Right?
Yeah, well, so we could find, it's just...
And so, what triangle might help us here?
3069.
Uh-huh. And so, okay, if this is, wait, hold up, which angle is which?
5 or 6 is small.
This one?
Yeah.
Are you sure? Are you right?
Yeah.
I want you to be sure, okay? Yeah. And this is pi over what?
3.
And what are my sides?
1 root 3, 2, or whatever order.
Yeah, which I do it in this order,
One
which
root
makes
two
that
root
2 root 3. And so then what sine of this number right there?
1 over 2.
Right? Because it's opposite over hypotenuse. And so the output here would be 1 over 2. And so as x approaches there, what does sine approach? What happens to sine?
Oh, it approaches what? 1/2.
Yeah. It's getting closer and closer. As x, and I guess in this case it's from the right.
Oh.
And this is kind of like what I was saying. You don't need to specify from the right for this one. Just because, like, same way with f of x, there's no discrepancy depending on what side you come from. So that could be a little weird. You might think, oh, is it different if I go from that way? Well, they're going to do that. They're going to try to trick you up, right? But this is the idea. As x goes to here, it's basically, see, they could have just, this question is the same thing as saying, what is sine of pi over 6? That's all they're asking. It's just, as you could see, you can't ask, what is cosecant of 2 pi? Because it's neither infinity nor negative infinity. But you could say, what happens if you approach from this way? Well, you'd go up to infinity. What happens if you approach from this way? Well, you'd go down to negative infinity. And so this direction we're approaching, this is actually important when it comes to things that aren't just straight up like things like f of x. Or things like sine. Sine is way easy. But yes, the answer here is that it approaches 1/2. Does that make sense?
Yeah.
Questions? Okay. So let's do one with secant. We have secant on the board. And so can I get rid of all this stuff down here, all this blue stuff? Everybody got this?
Yeah.
Okay.
So it would be the same, secant would be the same, just with cosine side. It would.
Oh, wait. I'm sorry. We're gonna do one of these. So, as x approaches, as x approaches pi from the right, cosecant x approaches what? Look at the graph, and this is why I want you to graph all of these. Because if you're not looking at the graph, you're wrong. Okay, so let's imagine.
Negative.
Yeah, so let's look at this. These are the as x goes this way, what happens to cosecant? Well, he starts moving down this way, and what is he getting closer and closer to? Negative infinity. You know, which is our shorthand way of saying it decreases without bound.
So when
it
sine
goes
goes
down forever.
up, cosecant goes down. And vice versa. Right.
Yeah. Depending on how you're talking about that. So sine going up here means that this is going down.
Yeah.
Sine going up here means, well, yeah, it's going down. When this is going down, that's going up. When this is going down, well, it depends on which way you're moving too, right? Like, so I would. This is why, like, if you try to keep in your head some nifty little thing like that. Well, when this goes down, this goes down. It could be difficult because if you're approaching from the right, maybe, but if you're approaching from the left, it might be different, you know. And so we just want to be careful with that. Okay, be very careful with that. So let's do as x, I do want to do this one. As x approaches pi from the left, cosecant x approaches what?
Positive infinity.
Positive infinity. Because, right, we're on this side of pi. This is what we're imagining, right? We see that. We think, okay, so you have some x value really close right here. And as you move closer that way, which direction does this guy move? Well, he goes up to positive infinity, or he increases without bound. Questions? Okay. Okay, so
What about tangents?
yeah, that's what we're doing right now. Right now. So, secant, which is 1 over cosine, is the same thing as if we just drew a cosine. And you know what? I might as well just real quick, we'll just knock that out because we do need, so we're all on the same page. Remember the black guy here was sine. Okay, and now I'm going to need a cosine. And I want to do this right here. 2 pi, 3 pi over 2 pi, pi over 2, 3 pi, minus pi over 2, minus pi, minus 3 pi over 2. Okay, so let's see if we remember. At 0, what is cosine equal to?
1.
Yes, 1. Okay? And it does this. It goes down, hits 0 right there. That's a positive 1. Do a negative 1 right there. Then it comes down and hits negative 1 at pi. Back up. And it has a period of 1. And so it comes back to where it started off after, I'm sorry, it has a period of 2 pi. So it has this type of thing. Now we're going to do this and this. This guy comes down like that. Comes through, -1. Okay. As you can see, I'm not going to be a stickler about if these are like how they're spread, but your minima and your maxima, the maximums and the minimums, and then where it goes through, that's important stuff. So if that's the case, let's think about the graph of secant. Secant x. Where are its asymptotes? Because we want to do this the same way. Let's get our asymptotes first.
Pi's over 2. And the multiple.
Yeah, all the multiple. So pi over 2 plus pi, right? Plus any multiple of pi. Okay, so I'm going to go ahead and draw the asymptotes first. In other words, wherever cosine goes through 0, you know that secant's going to blow up or blow down, depending on what side of it you're on. Okay, so we did last time we did asymptotes first. Then we did the parts that didn't move. What parts are not going to move here?
The 1s.
The 1s and the negative 1s are not going to move. So secant's going to go through there, and there, and there, and there. And then, now guess what? Is that the same thing as that? like qualitatively there's no difference. Like this just happens to be shifted a little bit, right? This just happens to be that thing just shifted a little bit. And so really this is super simple. Like once we get this idea in our heads about, and you approach from different sides, now it's really mindless. We could just do this. Okay? And really, that's how, if I had to draw secant x, this is what I would do. I would say, okay, hold up, I know that cosine does this thing. Okay, that's cosine. And so there's my asymptotes. Actually, the way I do it, sorry, the way I actually do it, is I draw a little dotted cosine like this.
Cannot draw a dotted line, is that?
Lots of practice here. Lots of practice. And so I get my asymptotes like that. And then I actually draw the thing I'm concerned about. So everybody's dotted. Now I'm going to blow up. And I'm going to blow down. This is going to blow down, and so on and so forth. This guy's going to come up, and so on and so forth. Oh, I missed a guy right there. Okay. That's how I would do it. You're gonna have to figure out the way that you like best. That's why you're gonna do this for every single one of these problems. And you're gonna be drawing this stuff so much in my class. It's gonna be ridiculous. Okay, so that's what secant does. So secant, cosecant, pretty straightforward stuff. And in black here we have cosine. Now let's do tangent. Because tangent is what over what?
Sine over cosine.
Yeah. Oh man. Okay. So that's going to be a little bit different. Let's go ahead and get this right here. So here's pi over 2. Pi. Okay, if this is tangent, we're going to draw tangent x. Where are its asymptotes?
When cosine equals 0, so.
There you go, because tangent is just sine over cosine. Wherever cosine is 0, this thing's going to blow up. And so, or blow down. And so, where is that? Where should I draw my asymptotes?
Pi over 2 and 3 pi over 2.
There we go. There we go. Right. The same places that cosine does. Right. So it blows up wherever secant blows up. It blows up whenever cosine is 0. So let's do it that way. Cosine is 0 here, so that's that, 0 here, and so that's that. Okay, now, how did I want to do this? Okay, now what we did with the other ones is we found the points that didn't move, and that made a lot of sense with sine and cosine. It doesn't make as much sense here. What I want to do is find the zeros of this thing. And I want to know, so I'm asking you right now, where is tangent equal to 0?
And sine equals 0.
There you go. Whenever sine is equal to 0, doesn't matter what's down here as long as it's not 0. But you'll notice that sine and cosine are never 0 at the same place. Right? Because whenever cosine is 0, you either have a max or a min for sine. Right? And so whenever sine is 0, you either have a max or a min for cosine. So, and yeah, if you remember that, that'll help you in calculus. So, again, where should I put my zeros for tangent?
Multiples of pi.
Okay, so is this one of them?
Yeah.
Is sine 0 here at 0? Yes, it is. Is sine 0 here?
Yeah.
Yeah. This is where graphs are your best friend, really, in this class. Like, and for the rest of your time in math. This is going to help you out a lot. If you could just look and see, okay, wherever that thing's 0, this thing's going to be 0, and so on and so forth. Okay, now, how did I want to do this exactly? So, okay, let's look at now we're going to determine behavior. And let's do it right here. Let's start at 0, and let's look at what's going on. As we move away from 0, we're plugging in bigger and bigger values. Sine gets bigger, right? Sine, the numerator is getting bigger. Okay, so in other words, as x is going away from 0, or we're approaching pi over 2 from the left, sine increases, right? So I'm just like, this is not official. I'm just thinking this is just what kind of goes through my head. Sine's getting bigger, right? Now what's happening to cosine during the same time?
It's getting smaller.
It's getting smaller. So as we move here, we can think about this as we move away from 0, we're successively taking a bigger and bigger number divided by a smaller and smaller number. What happens when you take a big number and divide it by a small number? Does it get smaller? Does it get bigger? It gets bigger, right? Because that's this is the same kind of thing that we saw earlier, right? When you start plugging in smaller and smaller numbers, 1 over that number, divide by a smaller number, it gets even bigger. So you're taking something that's getting big, dividing by something that's getting small, it's going to get bigger and bigger and bigger. And so what this looks like is that right there. It's going to increase like that.
Does it do it on here? Like,
What?
Does it do it the other way?
Well, we'll get there. Just hold up. So here's the thing, right? This shape right here, we do not have the tools at our disposal to show why it looks like that. And why it doesn't say do something like this and then go up or something. In calculus, you'll develop the tools to show that no, indeed, it must be the case that this thing looks like a cup on that side. We could go through and make a more careful argument besides these 2 arrows why that's the case, but it does curve upward like this, and it makes a cup in this direction. Kind of like if you think about it, it almost looks like qualitatively like a parabola, right? That it is the slope is getting steeper and steeper as you move this way. It never changes. It doesn't start getting steeper and then level off and then come back up, or start steep and then get like this. It has to be this way. But we don't have the tools to prove that in this class. But that's what it looks like. Now let's go in the opposite direction. Okay? Now as we go, we're taking sine over cosine. And now, x is going to approach negative pi over 2 from the right. So we're moving in this direction. Okay? So up here, what happens with sine? As we move in this direction, what is it doing?
It goes down to
It's
0.
decreasing. It's getting bigger numbers, but are they positive or negative?
Negative.
They're getting more negative. So it's negative, but the numbers are getting bigger, right? Okay. What's happening to cosine? All right, first off, are the values as we go this way positive or negative of cosine?
Positive.
They're positive, right? So you're taking, say, 0.9, then 0.8, then 0.7, 0.6. The whole time it's a positive.
But they're decreasing.
And they're decreasing. So then what's happening here? If not looking at the sign, is this thing increasing or decreasing in magnitude? Is it getting bigger or smaller?
Bigger.
It's getting much bigger, right? Because eventually we'll get to a point where you're taking like 0.99 divided by 1 over a million or something like that. And so it's going to get really, really big. But now you take a negative, divide by a positive, and is the sign positive or negative?
Negative.
Negative. And so we're getting bigger and bigger negative numbers as we go that way. And this thing, turns out, looks like that. Now just a note, again, we can't prove this in this class. What it does not do is flat like that and up, flat down like that. This is not what it does. It turns out that it goes through, and right there, right by the origin, it has a slope of about 1. Again, we can't prove it. We can't prove it. But if you were to zoom in really, really, really close right here, and you get closer and closer and closer, this would look like the pink thing right there. It turns out. I believe, let me see, you do plug in a 0 and you get a 1. Yes, it would be that guy right there. It would look just like the line y equals x. So, just so you know, I'm not going to be a stickler about it, but try not to, as you draw these, don't draw them like this, because that's just not what it does. It looks more like, when you're really, really close there, it looks like a slope of 1 right there. So, just so you know. Okay, so we did that part. Let's move over. Let's see what happens at pi. And let's do it the same way. Let's start at pi and move this direction first. We're going to move to the right. So we're going to take x approaching 3 pi over 2 from the left. Is sine positive or negative there?
Negative.
It's negative. Is cosine positive or negative there? It's
No.
what?
Oh. Wait, no, negative.
It's also negative. Because look at that. Like this is why I drew it this way. So you can just look and say, okay, as you move from here in this direction, cosine's negative and it stays negative. As you move from here to here, sine's negative and it stays negative. So you have a negative divided by a negative,
Positive.
which is a positive.
Yeah.
And your sine values are increasing in magnitude. So the sine values are increasing in magnitude. Yes, they're going. Yes, I know they're going down, but they're getting away from 1 over a million and getting closer and closer to 1. Down here, I'm sorry. Wait. Yeah. Okay. Yes. Okay. Yeah. Cosine, those values are decreasing. So you have a negative over a negative, which is a positive. And is the magnitude getting bigger or smaller?
Bigger.
Bigger. And so we have the same picture as before. What happens when we go the opposite direction? Now we're approaching pi from the right.
So cosecant is negative and sine is
We're
I mean
going
cosine.
there you go. Okay, so cosine is, you said negative?
Yeah, negative.
And is sine positive or negative?
Positive.
Positive. Right, so let's see. Yep, because we are here, and we're going in that way. So sine is positive and increasing. Cosine is negative and...
Also increase.
Oh, wait a minute. What are we talking about? Yes, no, well, yeah, increasing, but in magnitude, it's getting small. Yeah, I know. And technically, I'm wrong, because I shouldn't say that it's increasing or decreasing. The magnitude is getting smaller, and that's what we're talking about here. We're talking about like the absolute value of this thing, right? I know. So it's getting smaller, right? You're taking numbers like you start out at 0.9, then you're at 0.1. Then you're at 1 over a million as this thing happens. And so it's a negative number, and is it increasing or decreasing in magnitude?
In magnitude, it's increasing.
Yes. And so it's going to do this. And you could continue this on with everything.
Yeah.
And in every case, this is going to happen. So here's a question. What's the period of tangent?
When does it
How long does it, because remember the period is, how long does it take for it to repeat?
Oh, 3 pi over 2. Mm-mm. Oh, 2 pi, because it starts at
Nope.
pi, just pi.
Just pi, right? Because think about it.
Just pi.
Like this thing is the thing that reoccurs after pi. Whereas like with sine, it's like, oh yeah, it comes back to 0, but that's qualitatively different. Now you're at 0 and you're decreasing, whereas before you're at 0 and you're increasing. And so you had to wait until you got back to 0 a second time until now they're doing the same thing. In this case, it's just pi. That's it. The period of tangent pi. So that means, just like we discussed before, tan t plus pi equals tan t. And not just pi, but any multiple of pi. Okay? Just for every t in its domain. Not everything's in its domain, is it? That guy's not in its domain. That guy's not in its domain, and so on and so forth, but that's kind of, I mean, however, but if t does happen to be one of those, you'll still have an asymptote there. It's just that to talk about equals doesn't really make sense. Because what does it equal there? Is it positive infinity or is it negative infinity? We can't reconcile that. So there's that. Okay. Any questions? Any questions? Any questions? Okay.
Oh,
The only one left
cotangent.
is cotan. So this was tan. Now what we could do, because cotan is just 1 over tan, we could just take this and try to 1 over that guy, but though what might be nice is to see where would the asymptotes be. Just looking at this, if cotan is 1 over that guy, where are my
Same
asymptotes?
as cosecants. Sorry, cosines. Asymptotes, right? I mean, no. Secants asymptotes.
Would they? Because remember, so remember here. Let's look at it this way. We're doing cotan, which is 1 over tan. And so, what's the bad value, output value for this guy? Like this
You don't.
can never be what number?
0.
That can never be 0. So where does tangent equal 0?
When sine is 0.
Or how about just look at right here?
Oh.
Everywhere right there, right? And yes, there's another way we could do it, is we could say, this is the same thing as cosine over sine, and this is the way we're going to analyze this in just a second. So you could say wherever sine is equal to 0, which is at 0, pi, 2 pi, all the integer multiples of pi, and that's also the same thing as wherever this guy equals 0, which is at all the integer multiples of pi. So I'm going to start with my asymptotes. We have one here, we have one at pi, we have one at 2 pi, and let's go down to negative pi, and we'll do a negative 2 pi. Why not? Okay, now looking at this, cosine over sine, where is cotan equal to 0?
Wait. It would be
Cotan is equal to 0 whenever what is equal to 0?
cosine.
Cosine. Whenever cosine is 0, cotan is 0. So that means it's going to go through at the same places that cosine goes through. And so that's going to be here, here, here. And so I'm going to go ahead and put a dot here at pi over 2. I'll put a dot at 3 pi over 2. And so I guess I'll go ahead and put a dot at 5 pi over 2. A dot at negative pi over 2. Negative 3 pi over 2. Now, I'm willing to bet that this is going to look very similar to this. The question is, which way is it going to go up and which way is it going to go down? So let's start here at pi over 2. At pi over 2, we know that cosine is 0. Now let's move to the right. Cosine is negative. So we have a negative number. Is it increasing or decreasing in magnitude? Increasing. It's getting bigger in magnitude. Okay? Now, we're dividing by sine. So here, just to the right-hand side of pi over 2, sine is positive, and it's decreasing. So, right, this is what we're analyzing here. What happens as x moves this way? We have, is the entire thing positive or negative? Negative. It's negative, and is it getting bigger or smaller?
It's getting smaller.
Well, it's going down.
Yeah.
But it's increasing in magnitude. I know. I was like, really, this is like the one time that we'll have to deal with this. Because once you got these pictures in your head, if you believe it, you just knock it out, right? And so it does this right here. We could do the same kind of thing. I want to check our time. Okay, yeah, we're going to wrap this up. But with the exact same logic, we could figure out that this thing goes up and this way. And again, it's going to do the same thing. These things just repeat over and over again like this. And so it goes like that. This goes up like that. So basically with tangent and cotangent, all you have to remember is that one of them go up as you move this way, one of them goes down as you move this way. Tangent goes up, cotangent goes down. You have to remember where the asymptotes are, but once you've done that, halfway between those asymptotes is where it goes through. Pretty easy to remember. By the way, this is cotan x. Okay. What's the period of this guy?
Pi.
Again, pi. They're off by pi, right? You can see that by looking at the asymptotes or whatever. The only other thing I was gonna say, so there's a really nice table on page 441. I wouldn't memorize everything that's in it, because if you got these pictures, if you could derive this stuff, or if they're just so locked in your head, you could get all of that information, you know, like without memorizing a big, like, it's like a 12 by 5 table, like. You don't need to memorize it, but it's really good. I would consult with it. I do want to just say a couple things about the kind of stuff that's on there. And let's see if we can figure some of this out. So, sine, cosine, tan. We're going to go cosecant, secant, cotan. This is kind of what the table looks like. Now, let's see if we can figure some of this stuff out. So, remember this is tan. Now, domain, range, period. There's a bunch of other info here, but right now, I'm just concerned with these. Let's do the easy one first. Let's do period. What's the period of sine?
Pi. No, 2 pi.
2 pi. What's the period of cosine?
2 pi.
Period of tan?
Pi.
Pi. Let's go ahead and knock out cotan. What's the period of cotan?
Pi.
What's the period of cosecant?
2 pi.
2 pi again, right? Like, if you look at cosecant, you're like, okay, it does that thing. It does that thing. Oh, it's doing that thing again. That happened after 2 pi, right? They're off by 2 pi. Or you could, like, what's the distance between these guys? Well, it's 2 pi, right? So, yes, 2 pi. What about secant?
Also 2 pi.
Also 2 pi. And since these are just 1 over that, kind of have to have the same period. Ditto with this. This is just 1 over that, and that's just 1 over this. And so, yeah, okay. What's the domain of sine?
All real.
All reals. By the way, we defined it, right? We said we need to extend, we have this thing for acute angles. But how can we extend it beyond? Well, we could say you take any real number and interpret that as a turning around of, you know, whatever on the unit circle. And then you just take your that and that. And so yes, we have defined both sine and cosine for all real numbers. Now, what's the domain of tangent? And in this case, all I want to know are which ones, we're going to define it by what's not allowed. X cannot equal what?
Pi times n.
Pi is fine. I could plug in a pi.
Oh, pi over 2 plus pi times n.
Yeah, there you go. Pi over 2 plus turns out to be the period. Whatever the period is. That's, by the way, that's a pi times n. I could draw that better. I could totally draw that better. Pi times n. Where n is an integer. Any integer, right? Happens to be the period. Imagine that. Okay, so that's how we're going to do it in this class. If I say, what's the domain? If you tell me x, that I'll understand that what you're saying is all real values of x except for these. And that's what that is, right? And so, and indeed, just check that out, right? Go to here, add pi to it. Oh, you have another one. Add 2 pi to it. Oh, you have another one. What about What if n is -1? Well, if you're here and you go that direction by pi units, yeah, you're back at one of those. Okay, what about, what's the domain of cosecant?
No, wait.
There's certain things you cannot plug into cosecant.
Pi n. Pi times n.
Pi. So x not
Yeah, x
equal to pi times n. Because what happens if you try to plug in pi into cosecant?
Blows up and down.
Yeah, so we can't, even if we tried, we couldn't define what that is. So, okay, what about secant?
The same as tangent.
There you go. Right? Tangent has a cosine in the denominator. That's where it blows up. Secant has a cosine in the denominator, and so it's going to blow up the same places, pi n. And what about cotan?
The same as sine. Wait, no, the same as secant. Wait, no, the same as
Same as
cosecant.
cosecant. Yeah, so it cannot, and we could just look here and say, well, pi, 2 pi. Oh, all the integer multiples of pi. So x cannot equal n pi n, whatever. Now, range. What's the range
Allowable output.
of what's, yeah, so all the outputs that happen. When you take all of the allowable inputs and throw them into sine, we're going to take a look at everything that gets hit on the
Everything
y-axis.
less than 1, but bigger than negative.
So how would I write that in interval notation?
Oh. You use the
So,
union.
hard parentheses.
Yes, hard, because are the, okay, you tell me what to put in here and then we'll talk about
Negative 1.
it. -1.
Then,
To 0.
no, just
Wait.
1.
Oh, right, you just put one of them. Yeah.
And then
Just
hard parentheses.
hard, yeah.
Because, right, we're imagining the range is, same way with domain, you're looking at intervals here. Range, you're looking at intervals here. And I just imagine, okay, well then, since sine hits all of these, and look, we're including -1, because indeed there are values that you plug into sine and you do indeed get out a -1. -1 is an output, and so we are going to include it. What about cosine?
The same.
Same exact thing. Okay, so -1 up to 1. Okay, what about tangent?
Negative
like-
infinity?
It's the opposite. So it can't be anything between -1 and 1.
Tangents? Look at this. What gets
Oh,
hit?
I was thinking
What gets hit by a tangent?
Everything.
Everything.
Yeah.
All real numbers. In other words, you give me any real number, 700 billion, I could find you a value for tangent that will work. Every possible output is represented there. What about cotan?
Exactly.
Exactly the same. Okay, well, here's the hard one. What's the domain of cosecant?
It's soft bracket,
Yes.
negative infinity,
Yes. Soft bracket, everything from -infinity up to what?
-1. Hard
-1. Are you sure it's a hard bracket?
bracket. Yeah.
Because -1 is indeed an output. Then I'm going to union that guy with what?
Wait.
Hard bracket,
-1.
-1.
Oh, no, 1. You can't.
1 to
One.
negative.
To infinity.
Or
To infinity. Soft bracket. Because if you're looking at this, right, and here, I want to get this out of the way. So, this is what this guy looks like. And remember, domain and range, we're just asking ourselves, what values get hit? So, like, you plug something in, and this, you know, is one way of showing it. Another way of thinking about it is that this number right here, which happens to be 3 pi over 2, gets mapped, boom, to here, to -1. It's almost like you have an arrow pointing from here to here and asking, what number is going to hit that number? And, right, like one way I showed it is you could just think about, take all of your outputs and just project them on to the y-axis. And then ask yourself, what got hit? Well, everything from here, and now this is how I like to think about it, everything from -infinity up to here We're missing all these guys, but now we know that's 1, and so everything from here all the way up to infinity, those are my outputs. When you're asking about inputs, we could say, well, you can't include that guy or that guy. Can't include that guy or that guy. And like you were saying, we could, instead of writing it like this, you could write it with a union of infinitely many of those guys. And there's a nifty way of writing it. And you could just write, like the same way that we do pi n and stuff like that or that. You could do that on one side and then an n plus 1 over here, and it would be good. But, man, what a pain. It's much easier to just say that, and we're all on the same page. But again, it's good. When you see that, you should see this infinitely many things here. Or you take the entire real line and you're just deleting each of those, leaving you infinitely many open intervals here. The outputs are these half-closed intervals, right? So that's all we got for today. If there are any questions on the homework or anything you want to go over? These are difficult. I like that shirt. That's cool.
Oh, I've seen that.
Yeah.